Okay, I want to find the domain of f of x. F of x is a function, and the domain would be the input values to the function, or the set of allowable input values to the function. And so they're the x's, the x values that work, that give me an answer. We've talked about two different ways to exclude something from my domain, two different ways to have inputs that don't work, that give me values that don't exist or are not real. So there's two things we need to check for. Does the value exist, or is it real or not? In this problem, we have no radicals. So real or not is not an issue here, because we can't have the square root or the fourth root or an even root of a negative number, which is how we get non-real numbers. So we don't have to worry about complex numbers for this problem. We do have to worry about divide by zero errors here, or divide by zero undefined values here. And so what I need to do is I need to find all of the places where an x value would cause me to divide by zero. Well, the simple way to do that is to take the denominator of my fraction here. Don't care what the numerator is unless it lets me simplify this, which sort of, it doesn't restrict, it doesn't change the domain restriction. It does change the way the function behaves. So for this problem, it actually wouldn't change anything, even if the numerator let me cancel a zero out, let me remove a discontinuity. And that would just make it a removable discontinuity instead of a non-removable discontinuity. There are different types of discontinuities, but we'll get into that later. What I want to do for now is I want to take that denominator, I want to find out all of the x values that could make that denominator equal 0. Well, that just means take the denominator, x squared minus 4x minus 5, set it equal to 0, and solve for x. Because setting this equal to 0 and solving for x lets me find all of the x values where this whole thing equals 0. Well, if this whole thing equals 0, then I have 1 over 0, which is undefined. So the x values that make that whole thing equal 0 are the x values that I can't use as inputs. Okay, so I want to find the x values that I can't use as inputs. I do that by taking the denominator, setting it equal to 0, and finding the x values that make the denominator 0. Well, we haven't covered quadratics yet. So if I give you a quadratic like this, you really only have one tool to use, and that's principle of zero products, which means you have to factor. So if I give you a quadratic like this, until we talk about factoring, or until we talk about solving quadratics, I better give you something that factors, or I've asked you to do something I haven't taught you how to do. So what are we going to do? We're going to try to say this would factor. If this factors, there's a 1 in front of that x squared. So if this factors, it's going to factor into two binomials. And those two binomials, the first term of each is going to be x, because the first part of FOIL is first, and that would be x times x, which would give me 1x squared. Okay? Now I want to finish undoing the multiplication that left me with this x squared minus 4x minus 5. And that means that I'm looking for two numbers that multiply to equal my negative 5, and then add to equal my negative 4. And I can make a table of factors over here on the right, but this one's simple enough. I'm just going to go ahead and write in that it'd be negative 5 and a positive 1, because negative 5 times a positive 1 gives me negative 5. Negative 5 plus 1 gives me my negative 4. If you're unsure about that, multiply this thing back out, and you will get that polynomial. And it's always a nice way to check your factoring. All right, well, by the principle of zero products, I can break this into two equations, right? Because if this is 0, it does not matter what that value is. This 0 will wipe it out, right? And so the 0 will equal 0. This will be a true statement. And by similar logic, if this thing equals 0, it does not matter what that is. This 0 will wipe out whatever number is there, and I'll get 0 equals 0, which will be a true statement. So I have a possibility of up to two solutions here. I have x minus 5 equals 0, or x plus 1 equals 0. So I'm going to add 5 to both sides, x equals 5, or subtract 1 from both sides, x equals negative 1. All right, well, those are the two x values that cause this equation to equal 0. I can test that if I want to. I can plug in my negative 1, I could plug in my 5, and it'll work. Well, that means that those are the two values that I just can't allow into my domain. And so what I want to say is that my domain, there's a couple of different ways I can say this. I can use a set notation, or I can use an interval notation. If I use an interval notation, I'm going to say, so this is domain and this is interval notation. And I'm going to say we're running up from negative infinity. And remember, negative infinity is a constant, not a value. It's a concept, not a value. Sorry, concept, not constant. It's a concept, not a value. And so you can never reach it. So I use parentheses, because parentheses are for values you don't reach. Brackets are for values you do reach. All right, and I'm going to bring that all the way up to, but not include, negative 1, because I'm excluding negative 1. And remember that U without a stick means union. I told you to think or, because it's in the set on the left, or the interval on the right, interval on the left, interval on the right. Okay, and then negative 1 up to 5, but not including 5. Then union with 5 up to infinity, not including infinity. And basically I'm just saying from negative infinity up to infinity, I'm putting a hole in here at negative 1 and a hole in here at 5, because I can't have my values equaling negative 1 or 5. A more direct way to say that would be with set notation. And with set notation, I would say, so that's interval notation. This would be with set notation. And I would say that x such that x not equal negative 1 and x not equal to 5. Close the set. I'm not sure that one notation is longer than the other. I'm not sure that one notation is more convenient than the other. But math is a language like any other language. And I can't think of a language where there's only one way to say something, right? There's almost always more than one way to say something in a language, because in different contexts, one verbiage or one phrase may be easier or more appropriate than another phrase. And so that's part of why in some contexts interval notation is going to be better. In some contexts the set notation will be better. And so that's why we need to be able to read both. We need to be able to talk about both. All right, I hope that helps.